As I was driving over here, I asked my team what title did I give this talk, and they told me it, and I said that's a very ambitious title. So I'll see what I can do in the lead up to it. To explain something about my own trajectory, I started life as a physicist. Actually, I started doing that when I was pretty young, and I actually started my first company back in 1981, doing mathematical computation kinds of things. But our fine, forward-looking venture capitalists at the time said, you don't want to be doing mathematical computation in 1981, you should be doing AI. And in fact, the company eventually went public under the name Inference Corporation, which in today's world would be a nice modern name. But in 1983 or something, it was not quite the right time. I spent a large part of my life kind of trying to use computation as a way to formalize things in the world. So I kind of view thinking about sort of things one thinks about, human language as sort of a first example of a way that you formalize things, a way that you can, you don't just point at different rocks, you can have the word rock, and that sort of symbolically represents this idea of rocks. Then we get to logic, we get to mathematics, and the big thing of our century, I think, is the idea of using computation as this way to formalize thinking about the world. And so I've spent lots of effort trying to create kind of a computational language for describing the world in a computational way. And that computational language, we call it Wolfram language, has representations of things, not just things in a computer, but things like cities or diseases or bones or genes or whatever else. And it's able to compute with those kinds of things. And that's kind of the notion is there was, back in the day, people would do mathematics by just using ordinary language words, and then mathematical notation got invented, and that led to the creation of algebra and then calculus, and now all the mathematical sciences. The way we view what we're trying to do with our computational language is to provide sort of the notation for formalizing the world computationally that allows one to kind of build computational X for all X. So that's kind of that branch of things is thinking about how to formalize the world computationally. Once you can formalize things, you can build these big towers of consequences. You can do lots of sophisticated computations. Okay, so how does kind of modern neural net AI fit into all this? I mean, I first started playing around with neural nets back in 1981, and I couldn't get them to do anything interesting, and I kind of assumed they would never do anything interesting. And then 2011 came along, and neural nets suddenly were able to do pretty good image recognition. There was a big jump that happened at that time. This is sort of the characteristic thing, what I think one's seen multiple times. There's a big jump that happens. Image recognition today is not that much better than it was in 2011. There was a kind of a moment when things moved forward. There were moments when speech-to-text moved forward. Then 3 years ago, we had the moment when, to everybody's surprise, including the people who were working on it, ChatGPT came out and was able to sort of fluently write essays and so on. I think one of the things I was curious about is why does ChatGPT work? How did we, is it actually doing something hard? It's not obvious it's doing something hard because we don't really know how hard it is to continue a sentence in a reasonable way. And I think what I finally sort of concluded is that the way to think about it is this. It's when we have human language, we're used to kind of syntactic grammar of language. We know that sentences are constructed with noun, verb, noun in English. But in traditional grammar, we don't know which noun, which verb, which noun. What ChatGPT learnt from its training was kind of the pattern of kind of which noun, which type of noun, which type of verb, and so on. And so it's kind of using this kind of semantic grammar of language, which is something we could have discovered hundreds of years ago, but we didn't until the AI came along and showed us this is how this works. So there are a certain set of things you can do pretty well by just sort of continuing things in this kind of statistical way. You can get to kind of generate very reasonable kind of average text and so on. There are things you cannot do so well. You can't do things which require serious computation. The way I tend to think about it is, what's the heuristic for when something is going to work well with machine learning? Usually, it's if getting 80% success is a win, then use machine learning. If you need 100% success, don't try using machine learning because you will never get there. You'll keep trying to crawl up, trying to get, an extra percent and so on, but you'll never get that. If you want to get 100%, if you have a situation where you need to get 100% accuracy, you need something formalized, something computational. And that's kind of a thing that we see, well, so kind of the thing that is sort of an emerging direction is how do you combine the computational with the kind of neural net AI kinds of things. This turns out to be comparatively easy. The LLM produces, kind of gives input to, well, there are a variety of ways to do it, and this is sort of a technology we've released some things, and we'll have more things we're going to release soon that kind of help to let the LLM, to give the LLM clues for what the sort of results of computations are related to the kinds of things that it is thinking about, so to speak. I would say that one of the patterns, people say, well, we're not going to need programmers anymore, we just tell it, we do vibe coding, we just tell the AI what to do. That people are realizing that actually doesn't work terribly well, and I think the workflow that does work is to say, tell the AI roughly what you want, have the AI produce a readable piece of computational language code that you as a human can look at and say, well, AI, you understood that part correctly, that part you got wrong. Then you can take that piece of computational language code and make that a sort of solid brick that you can use to build your whole system. Having the, just sort of vaguely talking to the AI and expecting it to generate some huge blob of code and expecting it to be correct is hopeless, I think. If that works, the only reason it works is because the blob of code you just wrote is a blob of code 100,000 people have written before, and the AI was just able to copy it off the web. So, we're in this kind of interesting position because we've been building this kind of computational language that tries to formalize the world in the sort of as high a level a way as possible. So we're in this kind of unique position of having a language where the thing that gets written by the AI with lots of effort in hinting the AI to do the right thing is a piece of code that is very short, 2 or 3 lines long, let's say, and the human can actually understand. And so a human can take that and put it and build from it. I should say something about, let me say something a little bit more theoretical about computation versus AI and so on. Another thing perhaps to say about one question is why do LLMs work? I mentioned kind of the structure of language, but why does AI in general work? Why does an AI successfully manage to distinguish a picture of a cat from a picture of a dog? Even when you modify the pictures in different ways. I think the thing to realize is the reason that it seems like it's working to us is because it makes the same decisions that we do about what's a cat and what's a dog. Why does it make the same decisions we do? Basically because it's working more or less the same way we're working. It's the details of the neurophysiology of brains probably don't matter a lot for the kind of computation level of what's happening when you're doing those kinds of recognition tasks. So the reason the LLM is able to make the same distinctions we make is because it sort of works in the same kind of way. The things it's good at doing are the same kinds of things that we're good at doing, making these kind of judgment calls, things like this. If you ask the LLM to run code inside the LLM, it will do as badly at doing that as a human will do. Humans can't run code in their brains. People aren't able to kind of think through what a program will do in their brains. It's just not what we're built for, nor are LLMs. Sort of a different path. I view that sort of the most valuable thing perhaps about LLMs is they provide these kind of linguistic user interfaces that allow one to go from the way we talk about things to something that can be then put into a different form and, for example, used computationally. I mentioned one sort of theoretical kind of thing, and then perhaps we can turn this over to Q&A. But so, as mentioned, one of the things I've long been interested in is what one might call computation in the wild. We think about programs as being things where we write a program for a particular purpose that we have in mind. But what if you think about programs that are just arbitrary, simple programs that just pick at random? What do those programs typically do? So a big thing that I discovered in the 1980s is that even incredibly simple programs can do incredibly complicated things. And one of the things that one realizes from that is there's sort of a fundamental unpredictability to what can happen in many kinds of systems. I call it computational irreducibility. And it has to do with the following thing. Even when you know precisely the rules by which some system operates, you can't necessarily jump ahead and say what the system is going to do. You can always figure it out by just following the rules step by step and seeing what the system does, but you can't expect to kind of jump ahead. And in traditional science, mathematically based science, kind of one of the big ideas is you can find a formula for the answer and always jump ahead and see what the system is going to do. Many systems in nature and in the world, I think, are computationally irreducible in the sense you can't know what's going to happen without essentially running each step and seeing what happens. Okay, how is this relevant to, these kinds of ideas about simple programs and so on made some kind of breakthroughs about 5 years ago now in understanding fundamental physics in these terms. Didn't really expect this to work, but it does, and it's really exciting. But what is perhaps interesting is a spin-off from that. I also was saying, understanding fundamental physics is a thing for which there will be no application for 200 years. But I seem to have been wrong about that, because it turns out that the formalism that comes from understanding fundamental physics can be applied in a whole bunch of different areas. And last year I decided to try and apply it in biology. I had tried back in the 1980s to study how simple programs might do some kind of adaptive evolution that's like biological evolution. I didn't manage to make it work. I pushed the programs somewhat hard to sort of adapt and evolve, but I didn't push them hard enough. And the reason I didn't push them hard enough was because I didn't have the intuition that one has now from machine learning. The big surprise that was sort of the discovery of 2011 is if you bash a neural net hard enough, it will actually learn sophisticated things. That was not obvious at all. People thought, you do a simple experiment, it doesn't do anything in the simple experiment, it won't work any better when you do the more complicated experiment. That turned out not to be true. So I decided to bash some of these very simple programs much harder with sort of adaptive evolution. And I found that yes, you can get them to evolve. And in fact, what I discovered is that you can kind of understand why biological evolution works. It's not obvious that you can sort of get here from there, so to speak. That you can actually form complex organisms and things like this, that you can form things that have complicated behavior and so on. But what turns out to be the case, and this is this phenomenon of what happens is the reason that biological evolution works, I think, is that there's sort of this competition between computational irreducibility, a kind of computational sophistication of the underlying dynamics of what's happening, together with comparative computational sort of weakness of fitness functions that are used to determine what will happen. So to put it in a simple way, if biological organisms needed to be able to compute 1,000 primes to be able to survive, we wouldn't have any biological organisms. But it's because the fitness criteria for biological organisms are kind of mushy, that it's possible that there's sort of enough computational strength underneath that you can always find a way to satisfy those kind of mushy fitness requirements. By the way, the same phenomenon is the reason that machine learning works. You might have thought that with all the things that have been done in machine learning, that people would have a fundamental understanding of why machine learning works. We do not have a fundamental understanding of why machine learning works. I think I'm beginning to get some level of understanding, and I think the basic picture is this: that when you are, if you're trying to build, let's say you're trying to build a wall. You might build a wall by making bricks and then having these bricks carefully arranged, and that's how you engineer your wall. Okay, that's kind of strategy number one. Strategy number two, which is kind of the machine learning strategy, is there's a bunch of rocks lying around on the ground and they're all kinds of weird shapes. Those are kind of lumps of irreducible computation. And what happens in machine learning is you're picking up different lumps of irreducible computation and finding ways to fit them together so that the result is you more or less get a wall built. And so, when you ask, well, what's happening inside the machine learning system, it's hopeless to answer that question, because it would be like asking, why was this particular rock lying around at this particular time? That's not a thing you're going to be able to answer. But the fact that we can successfully kind of build this wall out of these rocks is a consequence of the fact that there's a certain supply of rocks provided by the way computational irreducibility works, and that the criteria we're using, the things we're trying to do with machine learning, are these comparatively coarse things. So it's okay. Having said this, I'll make one last comment about specifically about medicine, and we could talk a bunch more about this. But The question is, if you have this model for biological evolution, and you think you have some idea of how organisms that are fit for something get made, then the question is, well, what is medicine? What are you trying to do in medicine? And sort of a very simple-minded model would be, you have this organism, it's been evolved to live a certain time or whatever else, and when I say organism, I mean something that's a pattern of bits on a computer, basically. And then we say, well, let's perturb that organism, let's poke it in some way. That will prevent it from living its natural life, so to speak. It'll make it it'll make it fail in some way or another. So the first question is, when you poke it in different ways, what's the diversity of ways it can fail? That's sort of a classification of diseases of this computational organism. And it's quite interesting, because what you find is that, probably a little bit like you'd expect from experience of medicine, that if you kind of plot out in machine learning or something, what are all the different kinds of symptoms of things that can go wrong. There are islands that are fairly distinguished, which are sort of distinct diseases in a sense, and then there are these continuous pieces that kind of flow between different parts of this sort of space of possible things that can go wrong. So then the question is, then you sort of think of the fundamental problem of medicine ends up being, if the thing was perturbed and got one of these diseases, how do we put it back on track? Is there another perturbation that we can apply to the system that will make it go back to the way it was? Well, the main thing you realize is that's a hard thing to do. That's kind of in a sense, that's sort of why medicine, I think from the sort of computational point of view, why it's difficult. You can ask, well, what do you learn about what are the paths to make it easier, so to speak? You learn things like it's much easier to just sort of replace a piece of the system than it is to try and fix what's already there. Things like that. I would say that the general picture that I have, I've been curious about for ages, is when you think about human medicine or something, you're thinking about you've got the system and it's doing all the things we're doing, and eventually things fail. What about the computational analog of that? You've got a computer that's running its operating system, and the operating system runs for a week, and then it crashes. How does one understand sort of what can go wrong with the computer operating system? What's the analog of diseases in that? And this is something which I think we've got some understanding now from looking at these very simple models. I should stop yakking there, and I'm happy to have discussion, questions, whatever. That was a rough introduction for the kinds of things I think about, so happy to talk about lots of things. That's great.
Great, thank you. So a couple of questions from the hosts and then audience questions. And so my first question is, we're living in an age of AI innovation right now, and can we expect to get new medicine from AI? Or is AI going to give us good conventional answers but nothing new? Or will AI know all the data and all the current state of knowledge and find new things for us?
Okay, so I mean, the first thing to understand, I was sort of indicating this, is people say ChatGPT was very unexpected. We've got one data point. Let's extrapolate the one data point and let's take it to the moon, so to speak. I don't think that's what's going to happen. I think what we see with what's happened repeatedly with AI and machine learning is some particular modality gets figured out, and then there's sort of a jump in capability. And the LLMs of today are not that much better than the LLMs of 3 years ago. The way in which they're different is the harnessing of the LLMs has been done better. The things are in a better, they're sort of, the wild animal is still the same, but the kind of harness that's been put on it and the way that it connects to more traditional kinds of software technologies and so on is better. And the way it calls tools and the way it sort of stays on track and so on, those things are better. And it's also cheaper to run the LLM, those kinds of things. So first statement is I don't think, the idea, we've had this one data point, now it's going to go to the moon. I don't think so in this modality. There'll be modalities that show up, like I think robotics is going to get solved sometime. It's always hard to predict when these things will happen. But it's clearly on a path where, being able to have something which, a humanoid robot or something that can do the kinds of manual things that humans can do, that will come, and it will probably come fairly suddenly, perhaps fairly soon, for example. But that's just sort of a different modality. When it comes to, how, one thing, things like medical diagnosis, how will medical diagnosis be effective? I mean, one thing you realize is that medical diagnosis, it's not completely clear to me. Medical diagnosis is a weird activity because it's like, what I've learned from these kind of computational models of medicine is there's an infinite number of things that can go wrong. They are somewhat bucketed into these things that could have diagnosis codes, but that's really kind of an overlay on the details of all the things that can go wrong. My tendency is to think that eventually the picture will be that you measure a bunch of things, then you figure out what to do based on the things you measured, what the right thing to do is based on the things you measured, and the going through a diagnosis code is not really the important thing to do. And I think that will become clearer when there'll be a bunch of things that will eventually happen. I mean, there'll be whether we have sort of algorithmic drugs at the level of molecules, whether we have little nanobot-like things that interface, and these are the ways that we can expect to interface to biology in the future, beyond kind of just the static molecule that goes and binds to some particular site, in some particular place. I think that so I think the overall picture will be much more. We get a bunch of sort of sensor measurements, and we deduce what to do at a microscopic scale from that. How will in the way that medicine is practiced today, there are all kinds of things. I mean, I've been surprised that nobody has made, maybe somebody's done it now, a great medical history taking application with LLMs, because I think that's an obvious thing where you can have the LLM talk to a patient for an hour, and the patient will eventually mention, oh, by the way, I was in some rainforest last week, which they didn't happen to mention in the 5-minute discussion we would otherwise had. But I think that is using the linguistic interface capabilities of AIs, and I think that's an important thing in terms of can you do a better search of the medical literature? Given these symptoms or whatever, can you find things in the medical literature? It seems like what's being done. That seems like that's working pretty well. Will it be absolutely dramatically transformative? I doubt it. It may be transformative for places where people have no access to good diagnosis. But I think for the upscale communities, I'm not sure how transformative that will be. When it comes to things like discovering new drugs and so on, it is a little bit one has to be a bit cynical after all these rounds of rational drug design, combinatorial chemistry, this and this. And then it was, AI drug design from 5 years ago, and now it's AI drug design with generative AI and so on. Will this work? I don't know. I think that I don't think it is not something where it looks to me like it's an immediate, oh, this is going to be an amazing win. It's going to work great. The path from chemistry is hard. Chemistry is actually full of this computational irreducibility phenomenon that I was mentioning earlier, where it's hard to know what's going to happen until you effectively run it and try. And we still, there are endless things we still can't compute, and I don't think AI is going to help dramatically in that area. So a few thoughts. I think that in the a few initial thoughts.
Thank you. So for our audience, if anyone would like to ask a question, and if you do, raise your hand, say who you are, ask your question, and be loud. Anyone from our audience? Fanny?
Hi, apologies for being late. I actually know your work from college back in the 80s. I graduated in 83 and I worked with neural nets myself. Very pleased to meet you in person.